All right, so for these notes, we're going to make an outline of the periodic table, and we're not going to do the whole thing. All right, so this is similar to the periodic table that I had tucked into your notebook that you guys picked up at the beginning of the year. This would be a good time to start using that. Yeah, so what we're writing is going to go on page 23. So right next to the notes we took for this week. All right, so basically we're going to be drawing just a portion of this. Okay, so we're going to be kind of drawing this section of the periodic table. Okay, and remember when we do these columns and these columns, those are called the A group elements, right? And these ones in the middle here are called the B group elements. And so we can label these from 1 all the way through 18. But when we think about the elements in terms of A group and B group, the A group elements are just 1A, 2A, 3A, and so on until you get to 8A, okay? So it's just the A group elements that we're going to be looking at today. So we're going to sketch that on our notebook, and the way we do a quick sketch is to label the periods that we want to include. All right, and then we're going to do some columns. All right, these columns are our groups. All right, so there is hydrogen. Remember, there's only 2 elements in that first period. And then we have a step down for the second group. And then we actually have 2 steps down for these B group elements, which we're not going to draw. So I'm just going to do a little thing here to show that we're kind of leaving out a lot of it. All right, and then the periodic table kind of jumps back up, it kind of goes back up the stairs. And it does this for 5 periods, or 5 groups. All right, so that's 3A, 4A, 5A, 6A, 7A, and then 8A, that's where helium is, so we jump up that last stair. And when you're putting your element symbols in here, make sure you don't take up all the room, because we're going to turn these element symbols into dot diagrams today, okay? So now I'm going to go back in. And this is where having that periodic table that I had you pick up at the beginning of the year would come in handy, because you wouldn't have to wait for me to put mine in. You could just look at your periodic table and put your element symbols in there without having to stare at your computer screen. All right, so there's lithium in the second period, Be for beryllium, B for boron over here, C for carbon, N for nitrogen, O for oxygen, F for fluorine, and Ne for neon. Right, and then in the third period we have Na for sodium, which is kind of weird, right? Sodium starts with a S, but the symbol is Na because it comes from the Latin name Nasturtium. Let's see, and then Mg for magnesium. I'm not even sure I said that Latin name correctly. Al for aluminum, Si for silicon, P for phosphorus, S for sulfur, Cl for chlorine, and Ar for argon. I tried to find a chemistry joke for you guys this morning, but it turns out all the good ones are gone. Nobody got that? Nobody? What a shame. Michelle did. All right. So these are all the elements that we're going to make the dot diagrams for today. And we're also going to go in here and we're going to label the columns, right? So we're going to label this 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. All right. And so we're only looking at those A group elements. And this is just a reminder, we don't need anything here, but these are the B group elements here, the transition metals, and then those lanthanides and actinides at the bottom. They don't follow the really nice, neat pattern you're going to learn today, so we're just going to ignore them for now. And when you get to chemistry, you're going to learn a little bit more about them. All right. Okay, so I don't want to actually start the diagram part until everyone's ready. I don't want to leave you all behind. So let me know in the chat when you're set up like this and ready to go, because I'm about to give you some important stuff. Shell's done. Awesome. So is Dakota. Thank you. Brianna and Giselle. Carter, thank you. Let's see if I can zoom in on this a little bit more. I don't know. Thanks, Jared. There we go. Thanks, Morgan. All right, looks like we have about half the people. I know that was a lot to draw to set up here, but it's going to be worth it. So it's going to really help you out on your quiz, I think, too. Thanks, Naima. I think because of this distance learning, normally when we do stuff like this, if we were in the classroom, I would already have like little printouts for you to tape into your notebook. And I think the one upside to this distance learning is you've had to draw so many periodic table outlines that you guys are probably going to know it better than any of the other previous ninth graders. All right, I'm hoping everybody else is done or getting caught up. You'll be able to see this the whole time. So, excuse me. So the first piece of information we're going to add here is the rule that we're going to follow. Okay, so for electron dot diagrams, wait, was somebody adding something? Nope. Okay. This rule applies to the A group elements, right? That's why we're just drawing the A group ones. For the A group elements, the group number, okay, and I'm using the hashtag symbol for group number. The group number is equal to the number of valence electrons. Okay, and when we do our dot diagram, these valence electrons are going to be represented as, drum roll, dots. Okay, and we have been talking about valence electrons for 2 weeks now. It was like the only major vocab word that you had 2 weeks ago, the first week we did our notes back. right? So who can tell me what a valence electron is? How do we define that? Because it's a big deal. What is a valence electron? Any takers? Let's see. Eeny, meeny, miny, mo. Yeah, yeah. Hey, I'll let you pick, Mr. Jama. Oh, there goes Dakota.
I was about to give Dakota. She get it or she's not.
Yeah, so the electrons on the outermost energy level or ring, right? So let me give you an example. If we have the element sodium, right? So sodium actually has 11 protons, therefore it also has to have 11 electrons. And those electrons are going to exist in 3 energy levels, right? So we have electrons here, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons here, and we have 1 electron out here. This guy, the electrons in the outer energy level, are the only electrons that we can call valence electrons. All right, so that's what our valence electrons are. Those electrons are the only ones that participate in chemical bonding. So all of the compounds that you've seen so far when we did our exercise on Tuesday, and all the compounds we're going to be talking about, they form because of these valence electrons. Okay, so not because of the nucleus, not because of these electrons inside, but only what's on the outside. All right, so valence electrons, they create chemical bonds. All right, that's why they're important. That's why we're looking at these dot diagrams, okay? Because you're going to use these dot diagrams when we come back to predict the formation of chemical compounds. All right, so what this rule up here says, really, okay, because this is the entire focus of what we're doing here, is that all of the elements in column 1A have 1 valence electron. All of the elements in column 2, group 2, have 2 valence electrons. All of these ones have 3 valence electrons. And it follows that pattern. Okay, so what is the biggest number of valence electrons that you can possibly have given this pattern? Thanks, Giselle. Awesome. So we can only have up to 8 valence electrons. That's the most possible. And we can't have 0, okay? So it's from 1 to 8. And so now how do we represent those valence electrons? We do it with electron dot diagrams. And so X is going to represent a generic element. There are, there are absolutely no element X's. There's no X's anywhere on the periodic table, okay? Oh wait, I lied. There's xenon, but there's no just element simply X, okay? So we use this as a generic symbol for any element. And so for anything in 1A, it's going to have a single dot like that. Okay, so we're going to go over here and we're going to put single dots on these. And there's no right or wrong side. So you could put your dots on the side, you could put your dot on the bottom, or you could put it on the top, okay? It has to go on one of the 4 sides of your element symbol. All right, for 2. Now here's the trick. You can't pair them up. You have to separate them as much as possible. Pairs can only happen once you have a dot on each of the 4 sides first. Okay, so the next column is going to have 2 dots because there's 2 valence electrons for all of these elements. That's why they behave similarly. They have similar chemical reactivity because they have the same valence electrons. So they behave kind of the same way. Okay, I can draw my 2 dots however I want on whichever 2 sides I want. understanding that you can draw your dots on whichever side you want is important because when you go to see how chemical compounds form, you can save yourself a lot of long arrow drawing by drawing your dots strategically. Okay, and so for these ones, we're going to have 3 dots. I'm just going to go around with those. All right, and carbon and silicone, and really, so this pattern gets carried out all throughout the column. Okay, not just the ones that we're drawing, but down the entire column. Okay, so we'll have 4 dots here. For nitrogen, now that we have a dot on all of the sides, now we're going to go back in and we're going to pair one up. So this is really important because only electrons that don't have a partner get to participate in chemical bonding. Okay, so if we mess that up, then we mess up our thinking on how these elements can react with each other.
So we give some kind of pair up any side of the X, or is there a particular way to put it?
No, so you can put your pair wherever you want. So like I put it on top here, but I could put it on the bottom if I wanted to. So I can put my pair wherever, right? And so you're going to have 6 for oxygen. And my habit is I just go around clockwise and I keep adding them in clockwise because I know I'm not going to mess anything up that way. But that's not a hard and fast rule, right? Like if it's convenient for me to make my pairs on the sides, I can do that. All right, as long as we have a total of 6 valence electrons and 2 of them are paired up. All right, so then we're just going to follow that rule. I want you guys to don't do helium yet. Helium's a rule breaker. Okay? Not really a rule breaker in the sense of how we described it here, but it doesn't follow this nice pattern. So do fluorine, chlorine, neon, and argon. I'm just going to be quiet for a moment and let you see if you can do it correctly. It's really hard for me to be quiet. I've gotten into the habit of talking a lot. All right, so hopefully for 7A and 8A, for 7A, you had 3 pairs in a single. All right, give yourself a pat on the back if you got that, if you can reach. And the last column is special, okay? So it has no unpaired electrons. So take a guess at what that means. If you have no unpaired electrons, how are you going to be different as an element from all the other elements? This is a really high-level question. Yeah, so there's pairs on every single side. That is important. Okay, what does that mean? Remember I said wherever you have a single electron, there can be chemical bonding happen, right? So how does that make these different? Right on, right? If there's no single electrons, these can't bond with anything. And whenever I say can't, always take that with a grain of salt, because there are exceptions to every rule. But in general, anything in this column is not going to bond with other things. They're very inert. they don't react with things, okay? So we're going to say in column 8A, these elements here don't do chemical reactions. Okay, there's a special word. It's inert. It means it's not reactive. Okay, and now let's get to helium, because helium is different. All right, so remember when we learned how to make the Bohr models? We learned that the first energy level here, 1n, the first energy level can only hold a maximum of 2 electrons. It was the weird one. It's closest to the nucleus, therefore it's the smallest amount of area. Can only hold 2. So helium is, its outer energy level is full when it has 2 electrons. Okay, so for helium, we're going to pair those 2 electrons up because it's already full. Okay, so it's not going to be reactive. All right, so helium is the odd one. Alrighty, so that's it for our electron dot diagram review and practice. I am going to grab one thing to show you because I told you I would. So let's see if I can find it quick here. I'm going to bring back the periodic table of aliens that we did. Let's see if I can grab the right one here. Hopefully. All right, and then I said I would explain to you guys why this alien was so weird. So based on what we just did with our notes, does it make sense now why these guys all have 1 antenna, 2 antenna, 3 antenna, 4 antenna? Yet we get to this alien who clearly belonged here, right? He's got the facial expression, the same pattern on the body, 1 arm, but only 2 antenna. Okay, so what did these antenna on their head represent? Let me pick on Naima. Naima, what did the antenna on the aliens' heads actually represent? Helpful hint, we were just drawing them. The dots, absolutely. Okay, so the antenna were your valence electrons, right? And so that's how this alien fit there, even though he had 2 antennae and not 8. Okay, because he was kind of like hydrogen. All right, so that is it for your notebook. We have, remember, the classes go until 9:45 now. So we are going to go a little bit past 9:30 for our synchronous time today to do that Kahoot. All right, and so once we're done with the Kahoot, then you guys are free to go and go take care of your quiz for this week, because once you see the Kahoot, then the quiz is going to be totally easy, right? As long as you feel like the Kahoot is easy.